All right, welcome back to ECE484, fall 2021. So let's review what we did during our last lecture. So we finished up chapter 3, which was a chapter on a continuous time control design technique called pole placement. And the last thing we did is we were designing pole placement controllers to meet transient specs by placing the poles correctly, but also tracking specifications. And so the last thing we talked about was so-called practical step tracking, which essentially was our way of saying that we allow non-zero steady-state tracking error for steps. Okay? And so we derived the design equations, and we did an example. Then we moved on to chapter 4, where essentially we're going to take the controllers like the ones we designed in chapter 3, and now we want to figure out how to implement them on embedded computers, on a computer. Okay? And so the problem boils down to, in this case, given a continuous time design like this that you've designed, pick the sampling rate for your sample and hold blocks, as well as the digital control law, so that ideally this system here closely approximates the continuous time system, right? We mentioned last time, and you showed in problem set 1, that it doesn't matter what you choose D for D here. The overall system over here is from the tracking error E to the control signal U is going to be time varying. It won't have a transfer function, so you'll never get equality here. It's just not possible. Okay, so we need to do something. And we mentioned the main techniques, one of them being numerical integration, and that's what we started talking about. And so to motivate kind of what's to come, we've considered this simple controller, the integrator. We wrote down what it stands for, right? So if you integrate in the time domain, this is what that controller is doing, right? Over any interval of time from t0 to t, that's what the controller block is doing. And in particular, if you consider over a sample period, right, so over one t-second interval, you get that the difference of the control signal at time kt, remember k is an integer, t is the sampling period, minus the control at the previous sample instant is equal to this integral. Okay? But the problem with, like, if we could get that integral exactly, then we could implement the continuous time controller exactly, right? The rule would be my current control value is equal to the previous control value plus this integral. However, as illustrated in the figure on the right, we don't know the tracking error between samples. So we need to approximate that integral. We know E at the previous sample step. We know E at the current time step, but whatever's happening in the middle, we just don't know. And so we need to make an approximation. And so that's what we're going to do today. And I mean, it's kind of, you can imagine what we're going to do, right? We're going to do a bunch of 3 approximations, and the approximations are going to boil down to keep the value of the previous sample constant over the period, keep the value of the current sample constant over the period, or do linear interpolation between the samples. Right? And those are going to be our 3 numerical integration techniques. And that's what we'll see today. Okay, so let's get going. So this figure here, I'm going to come back to it each time we do an approximation. I'll use this figure here. So the first one we're going to do is the so-called left side rule. This is also Euler's approximation for differential equations. Okay, so as the name suggests, what we'll do, because we don't know the tracking error between sample periods, what we're going to do is essentially maintain this value constant. Oops. So, in other words, that area under that purple curve, which we cannot compute exactly, we're going to approximate it. Oh, sorry, this picture is incorrect. Sorry, let me fix this picture up. So that's the setup. And we're going to use that rectangle as the area under the curve. So it's the left side rule because we're holding the value of the left side in this figure constant over one period in the absence of information between the samples. And so what we get from this rule is that the integral that we're trying to approximate is just the area of a rectangle. So the height is ek minus 1, and the width is t, so it's just t times ek minus 1. So that's the approximation. Okay. Now, going back to our control law, remember our control was the current value of the control signal equals the previous value of the control signal plus this integral. Okay? If we use this approximation, we get the controller. That UK is equal to the previous value of the control signal plus t times the previous value of the tracking error. Remember, E is the difference between R and Y, the reference and the measured output. Okay? And so I'll just mention here, and we'll talk more about this as we go through, but this is the thing that you implement. Okay, I'll mention more about this as we go on. Okay, but I would like to take this kind of numerical approximation, I'd like to apply it to arbitrary controllers. So not just this simple integral controller that we're doing. And so let's figure out what this rule does to the Laplace transform, or to the transfer function of a controller. So I kind of warned you last time, we're going to use a little bit of discrete time theory here, and so it's very mild, and we will review it, but just be aware. So take the Z transform of that above equation. And again, we'll review in chapter 6. And what do we get? We get that U of Z equals, going backwards in time in the discrete time domain is like multiplying by, or dividing by Z. So we're going to get Z inverse U of Z plus Z inverse T E of Z. Okay, so let's rearrange that to get our transfer function from the tracking error E to the control signal U in the Z domain. Right, so this gives So stepping back now, we started off with a continuous time controller whose transfer function was 1 over S. It was an integrator. We used this left side rule, and we ended up with a digital controller, or a discrete time controller, whose transfer function is this quantity here. And so one way to think about this is we've taken the C of S, the S domain transfer function, and we've replaced S, the Laplace variable, with a function of Z, the Z transform variable. And so that's going to be our approximation. So the above is just our original controller, which was 1 over S, where we made the substitution everywhere you see an S, you replace it by Z minus 1 over T. And this is indeed our left side rule. Okay. So the left side rule, this numerical approximation we've done, just says, take your continuous time controller, replace S with this function of Z. Now you have a discrete time transfer function, and then you would turn that back into the time domain to get your difference equation that you implement. Okay. So let's do an example, just to kind of see how this would work. So again, examples without numbers means that they're not in the notes. Okay, so let's do a PI controller. So say you've done your third-year control type design, and you've come up with a PI controller, KP being the proportional gain, KI the integral gain. And now you want to implement it on a computer. So if we were to use the left side rule for this implementation, what do we have to do? We have to take S, and we replace it with this function of Z. So this would give this would give right, if we're using the left side rule, that's what we do. We take C, we replace it with this function of Z, and what you will get is this guy, of course, and that's our controller. And so if I put that over a common fraction, I can say that U of Z the Laplace transform of or the Z transform of our control signal is equal to this discretized controller times the Z transform of the error. Plug in the data, so you get so there's our discretized PI controller in the Z domain. Remember, T is the sampling period, right? So the control depends on the sampling period. Okay, let's go back to the time domain. So I'll remind you, I'll do this one in a little bit more detail, how you would do that. If I kind of clear the fractions, I'm going to get on the left-hand side, I'll get Z U of Z minus U of Z equals K P Z E of Z plus KIT minus KP E of Z. Right, so kind of doing this in gory detail, but nevertheless. Okay, so I've now written this, and now I want to go back to the time domain. So it's convenient. I mean, you don't have to, but it's convenient just to divide by Z at this point. Otherwise, well, you'll see in a second why. So I'm going to divide by Z. Okay. And now we have something which is hopefully sort of recognizable as what it would be in the time domain. Remember, dividing by Z is like going back in time, discrete time. And so we get our final rule. That the control at time k is equal to the previous control plus Kp times the current value of the tracking error plus KIT minus KP of the previous tracking error. Okay? And so this is a PI controller, which we've discretized using the left side rule. Okay? And so the block diagram would look something like this. Not the best box. Let's try and do that again. Okay, and in that box, we will have this difference equation. Okay, so this signal here will be EK, which equals E at the sample instant, the current sample instant. The thing coming out of the control block will be UK, right? And of course, that means that this is going to be equal to U. Well, I won't write it. It's the whole block. You know what it is. And then inside, we have this rule. Okay? And that's how we would implement this PI controller. Okay? So a simple discretization method, left side rule. Okay. Okay, so that's one method. Obviously, in this left side rule, we kept the left side constant over that sample period. For the right side rule, we'll keep the right side constant, and we'll get a different discretization rule. Okay, and so I'm just going to go up, grab that picture of the thing, this integral that we're trying to approximate, and I'm going to just bring it down here because okay. Okay, so there's again the integral we're trying to approximate. Previously, we had held the left side value, the previous sampled value of the tracking error constant. Now we'll hold the current sampled value of the tracking error constant. And so what we'll get is that we're going to approximate the area under that purple curve as being the area of this green rectangle. Okay, so it's certainly another valid, it's another way of approximating. And so with this rule, our integral that we've been trying to approximate, again, it's the area of a rectangle, but now the height is a different value. So it's going to be T times EK. And our simple integral controller now is that the current value of the control is equal to the previous value of the control plus this approximated integral. So this yields okay, so it's very similar. And we're going to do the same thing we just did. So we'll go to the Z domain, we'll get a function of z, and then we'll use that as our kind of replacement. A function, we'll take s and we'll replace it with this function of z, and that's going to be our right side rule. Okay? So doing the exact same thing we did before, we'll get that u of z is equal to tz over z minus 1 ez. Okay? So this is our discrete time version of the integrator when using the left side rule. Okay? And so that's our d of z. And we get the same, or a similar thing. So this gives the discretization rule s equal to z minus 1 over tz. And that is our right side rule. Okay, so we have now a second approximation technique, and we'll compare them. I'm going to list three, and then we're going to compare the different techniques. But for now, we have this right side rule. Okay, let's go back to our PI controller example and see what the right side rule gives for the PI controller. So there's the PI controller. I'm going to do the right side rule in this case. So right side rule gives that d of z is the following. So there's our discrete time transfer function. Again, we'll review discrete time transfer functions, but hopefully from the examples you get this idea that z in discrete time acts as like an advancing time or reversing time operator. Okay, and this gives us the controller in the time domain that looks like the following. That's the difference, the underlying difference equation in the digital controller, the discrete controller. Okay, so that is the right side rule. And so the last one we'll talk about is the most popular, kind of one of the most standard ways of discretizing, and that is instead of holding the value of the tracking error constant over the integral, we're going to do linear interpolation. Okay? And so that is called the trapezoidal rule. Also the bilinear transformation. All right. So again, I'm going to go back up, grab that image of the integral that we're trying to approximate in this section. Okay. So in the trapezoidal rule, as the name suggests, we're going to use the following. Okay, and so the idea here is we're going to approximate the area under the purple curve using this figure here. And so that's our approximation. And so what we're saying is that this integral is now approximately equal to the area of that rectangle of height ek minus 1 plus the area of this triangle. Okay, and I mean, you should note, of course, that the slope here of that line is simply the difference between the sample values of the error divided by the sampling period. Okay, so using all that information, you can verify that what you will get is t over 2 ek plus ek minus 1. Right? And you should verify that. Okay, so that's the trapezoidal rule, and so if we plug that into our simple integrator controller, we get a certain expression. So this approximation yields the following. Okay, so I'm taking the original non-approximated integral controller that we started with and plugging in the approximation, in this case corresponding to the bilinear transformation. Okay, and so again, doing the same thing we did before, go to the Z domain. Our controller looks like this. Okay, so that's our continuous time integrator discretized to get this controller here, this digital controller. Okay, and so doing the same thing we did before, we can turn this into a rule of, given a Laplace domain transfer function, replace S with a function of Z and generate a discrete time transfer function. And that's the rule that we'll write. Okay, and that is our trapezoidal rule. So again, if you've taken a numerical methods course, you probably have seen all this before, but we go over it again anyway. Okay, so let's do our PI controller again. We've done the PI controller for the left side rule, the right side rule. Let's finally do it for this trapezoidal or bilinear transformation. So there is our PI controller. We will do the bilinear transformation. get a digital controller, d of z, which in this case looks like, okay, so it's a little bit more complicated. See, kp plus kit over 2 z plus kit over 2 minus kp in the numerator, the whole thing divided by z minus 1. Okay, so nothing as fancy is going on there. I'm just replacing s with that expression from above and then rearranging the terms. And so if you were to write down the difference equation, you get so there's the dependence on the current value of the tracking error plus the previous tracking error. All right. So, so yeah, that's the bilinear transformation. So you see that the simple integral controller, we have different ways of implementing it, and it's true for this rule applies, of course, to arbitrary controllers as well. I'll mention that, you know, MATLAB, of course, can do this type of transformation for you. So MATLAB can do this. It's the C to D command with the Tustin option. Right? So if you do this, if you run the C to D command on a continuous time transfer function in MATLAB with the Tustin option, this will give you the bilinear transformation or the trapezoidal approximation. Okay. So we've got 3 different methods. Let's see, kind of compare them to see which one is better in some sense. So comparing the approximations. Okay, what would we like of these approximations? Well, I'm going to list 2 properties. You might be able to think of others. But one, we would like that as the sampling period gets smaller, in other words, as we sample in faster and faster, the approximation gets better and better. In other words, our discrete time controllers get closer and closer to the continuous time controller we started with. Okay, that's one property. So let's say that their 2 desirable properties are first, it's the one that I just said, that as t approaches 0, in other words, as you sample faster and faster, the approximation error sorry, I think I just had a technical issue here. Sorry, I just need to fix one thing. I've got a small glitch here, so 1 second. Sorry about that. Okay, I think we're back in business. We're doing this discrete time approximation, and one of the properties that we said is that the approximation error should go to 0 as t gets small. So the approximation error approaches 0. Okay. Secondly, what does this approximation do to the poles of the controller, right? So we're approximating controllers here. So if we have a controller which is stable in continuous time, it would be nice if the approximation technique preserves that stability, right, of the controller, right? This is not the closed loop system. So we'll call that preserving stability. So preserves stability. And by that I mean the continuous time controller is stable. If the discrete time approximation is stable. Okay. Again, this is the controller, not the loop. We'll come back to that point later on, but okay. So from the pictures above, you can probably convince yourself that for reasonable signals, so reasonable tracking errors, all three methods will satisfy condition 1, right? For realistic E of t, all three satisfy the first condition, right? But only the bilinear transformation satisfies the second. Okay. So let's try to understand maybe why the bilinear transformation preserves stability. So suppose C of S has a pole at S equal to lambda with real part of lambda less than 0, right? So C has a stable pole. So I'll draw that picture. So we've got a pole over here at lambda. Now, if I so yeah, okay, let me write that down. So the next comment here would be, under the bilinear transformation, which is that rule that we just derived, the most recent one, d of z which is just C of S, where we've made this substitution, we'll have a pole at the following location. Okay, so I'm just plugging in S equal to lambda in the rule and then rearranging for Z. Okay, so that's where the controller in the discrete domain will have a pole. So let's go back to our picture from above and do a little bit of geometry. So again, the controller has a pole at lambda with real part less than 0, and so if I multiply lambda by t over 2, sampling period divided by 2, its real part is still going to be negative because I'm multiplying by t, which is positive, over 2, which is positive. Okay, so let's call this x that I've drawn here t over 2 lambda. All right? And so let's look at the pole of the z in the z domain. It's right here. So I can think of this geometrically as vectors in the plane, right? So vectors in the S-plane. So what are these vectors? Well, the numerator I can think of as this vector. One plus t over 2 lambda. Okay. The denominator I can also view as a vector from a one point to another in the S-plane. And it's going to be this guy. One minus t over 2 lambda. So from this picture, hopefully you can convince yourself that the fact that lambda is in the left half plane, in other words has negative real part, means that the length of this vector is always going to be shorter than the length of this vector. Okay, what does that mean for our digital controller? It means that the magnitude of this pole location is going to be less than 1, because the magnitude of the numerator, this vector here, is going to be less than the magnitude of the denominator, that vector there. Okay, and so the magnitude of this pole that we just got after our approximation is given by the magnitude of the numerator divided by the magnitude of the denominator, and clearly from the picture above, we have this constraint, and so and therefore, d of z will be stable. The pole will be stable for d of z. Okay. One thing that, again, we're going to review in Chapter 6, but this is, I guess, a reminder here. This is another point where we're using a little bit of ideas from discrete time systems. Stability for a discrete time system, it doesn't depend on left half plane, right half plane, like it does for Laplace world. It depends on whether or not the poles of the transfer function are inside of the unit disk. In other words, have magnitude less than 1, right? So, again, we'll review this in Chapter 6, but the basic idea is that if you have a linear discrete time system, it will be Bibo stable if all of its poles have magnitude less than 1. Okay? And so this discussion here, what we've said is that if the controller in continuous time has a pole with negative real part, then the discretized controller, using the bilinear transformation, will have a pole magnitude less than 1. And it turns out vice versa as well. So the bilinear transformation preserves stability in this sense. So just point out that the bilinear transformation preserves stability of the controller. Stability of the controller. Not the loop. Okay, so be aware of that. Whether or not it preserves stability of the loop will depend on the sampling period, right? If it's sufficiently fast, and we'll talk about that in a bit. Okay, let me draw a picture here. I'm just thinking about maybe skipping this, but you know, it's probably a good place to end this lecture, and it's a nice picture. So I want to draw a picture now of the three numerical integration methods we've discussed, and sort of the way that they deal with the mappings of poles and of poles. Okay, so I'm going to make sort of like a chart here. On the right-hand side, or the left-hand side, I'm going to have the various rules that we've derived. Here I'll have the equations. And then I'm going to draw regions of either the S-plane in continuous time or the Z-plane in discrete time. So which is in the S and Z planes. Okay, and hopefully as I start drawing these things, it will make sense. So just to remind you what we've done, we had the left side rule. We had the right side rule. And the bilinear. Okay, those are the three rules we discussed. In the case of the left, we derived the following equation, z minus 1 over t. If you wanted to go in the other direction, you could find z as a function of s, and you would get z is equal to ts plus 1. Okay. And so I'm going to use those equations to map different parts of the s-plane to the z-plane, and vice versa. Okay, for the right side rule, we derive the equations That's the equation we derived for the right side rule. Solving for z gives (1 over 1 minus ts). And for the bilinear transformation, this is the equation we derived. Solving for z gave us okay, so those are the rules. And so over here in the last column, I'm going to draw a bunch of copies of the z and the s-plane. So the s-plane will be on the right, the z-plane are on the left, and the s-plane will be on the left, the z-plane will be on the right. I'll label that. Okay, so again, on this side, s-plane, on this side, z-plane. Sorry. I'm going to remove my camera for a second. Okay, so let's go through what these different regions look like. So in the for the left side rule, what happens is the stability region of the z-plane is this circle. Okay, and then the question is, which points in the s-plane get mapped to that circle, right? Because again, if the digital controller has its roots or its poles in that circle, then it's stable. Well, it turns out over here, you get a circle as well. Oops. And so this is the circle. In the s-plane. So what we're saying here is that all those points in the red circle, in other words, all those pole locations in continuous time, get mapped to the stability region in discrete time. Okay? And so it won't preserve stability. What this tells you is that there are stable pole locations out here in the S-plane, which will be mapped to unstable parts in the Z-plane. Okay? So in this case, we only get the following implication. That if d of z is stable, that means that c of s must have been stable. Okay? And I've run out of time, so I'm going to continue the picture next time, and then we'll talk about model matching methods for discretizing continuous time controllers. Okay, so we'll stop there. Again, we've been looking at numerical methods for discretizing continuous time controllers, and we are going to continue doing that next class, which I guess is next week. All right, I'll stick around for a couple minutes, but otherwise I'll see you next week.